So what we're looking at today, we've had these waves that we're looking at, and there's our typical sine wave, and we've talked about the features. The period. The period is the time it takes to complete a single wavelength. Now we've talked about a wavelength already, and the wavelength is just going from one spot on one wave to that equivalent spot on the next wave. Usually we take the equilibrium point. That's a wavelength. The period is as this wave is traveling, it is the distance it takes, or the time it takes for that wave to travel a full wavelength. So it's the time for one wave. We have a frequency. Now we looked at frequency as the number of waves in 360 degrees. Technically, frequency ends up being in waves per second. There is a direct relationship here. If frequency is the number of waves that go past in a second, let's say the frequency is, let's just go 20 hertz. Hertz just means per second. There's 20 waves per second. If there's 20 waves per second, the period, the time it takes for a single wave would be 1/20th of a second, right? So the relationship that develops there, or exists there, I should say, is the frequency, F, stands for frequency, is equal to 1 over the period, the reciprocal of the period. So T is period, F is frequency. So if the period is 2 milliseconds, what's the frequency? Well, the frequency is 1 over 2 milliseconds has to be, remember, frequency is per second. So we have to express the frequency in seconds, which would be 0.002, right? 1 divided by 0.002 is 500 per second. 500 per second is 500 hertz. If F is equal to 1 over T, if we set that up as a proportion, we can cross multiply and divide. I wanted to solve for T. What's 1 times 1? 1 divided by F. T is equal to 1 divided by the frequency, which makes sense. If the frequency is the reciprocal of the period is the reciprocal of the frequency. So what is the frequency of power coming out of a wall outlet? AC power. 60 hertz. 60 cycles a second. So what is the wavelength of the, 1 over 60 hertz. 1 over 60 is going to be 0.0167 seconds, or 16.7 milliseconds is the period. So every 16.7 milliseconds, a complete sine wave goes through that power outlet, or whatever device you're powering with it. Velocity. Let's say you're walking. And every step you take equals 3 feet. And you are walking at a rate such that you take, in the course of a minute, you take 40 steps per minute. What is your speed? What's your velocity here? How fast are you walking? Yeah, 3 feet per step. Put it as 3 feet over 1 step times 40 steps per 1 minute. The steps cancel out. 3 times 40 is 120 feet per minute. It makes sense. You just multiply the length of the step times the number of steps per minute. Makes sense, right? Well, if I'm looking at a wave, what part of a wave equates to like the length of a step? The wavelength, the length of a single wave. The number of steps per minute or per second in this case would be the frequency, the number of waves per second. So the velocity of a wave we use that script V. I'm actually going to write it like this just because I don't want it, so I don't have to draw it out. That's the script V that we use to represent velocity of a wave is the wavelength. We use that, that's the Greek letter lambda for wavelength. We're still going to use F for frequency times the frequency. Anybody know the speed of light? I want to say it's 300,000 kilometers per second. Yes, 300,000 meters per second. No, 300,000 kilometers per second, 300 million meters per second. So 300 million meters per second. That's the speed. What's the frequency of like a standard radio channel? What's your bandwidths? Give me a cell phone frequency. There's a reason I'm asking. Uh-huh. Cell phone frequencies. 800 meg. What's megahertz? Mega is million, right? Kilo is 1,000. So 800 mega is 800 million hertz. So the wavelength of those waves, if V is equal to wavelength times frequency, if I wanted to solve for the wavelengths, I would divide by the frequency, right? The wavelength is equal to the frequency divided by the velocity. Other way around, velocity divided by the frequency. So 300 million divided by 800 million is 0.375, and that is in meters. So 0.375 meters is the wavelength of those waves for cell phone transmission. What do you guys think? So what we're going to look at is rotational angular velocity. And angular velocity is basically, it's the velocity of things that are in motion, spinning. So I have something that's going in a circle. And let's say that this circle has a radius of 1, let's just go 1 unit, we're going to call it. That might look familiar. Unit circle, right? Let's say that we go around this circle. I'm going to go 50 hertz, 50 times per second. So the linear velocity is going to be the distance traveled divided by time, right? Well, our time here is 1 second. Our distance is going to be the circumference of the circle times 50, because it goes around that circle 50 times. The circumference of that circle is 2 pi, correct? Diameter is 2 if the radius is 1 times pi, that's the circumference. So the distance traveled is 2 pi times 50. Otherwise known as 100 pi. So the velocity of this thing 100 is 100 pi, or 314 divided by 1. So that is in units per second. That would be the linear velocity. But since this is going in circles, we can talk about the rotational or angular velocity. One thing that we've already actually talked about what's RPM stand for? Revolutions per minute. It's going 50 RPMs, 50 actually not revolutions per minute in this case, it's revolutions per second. 50 RPS, revolutions per second. It'd be 3,000 RPM times 60. Each revolution is 2 pi radians, isn't it? One revolution is 360 degrees, 2 pi radians equals 360 degrees. So the number of radians, the rotational velocity, is in radians per second. Two pi radians for one revolution times 50 revolutions is 100 pi radians per second, or 314 radians per second, if you wanted to write it that way. Why is it that the rotational velocity and the linear velocity are the same here? Well, because what's the radius? 1. The radius is 1. So there's a relationship that's developed here between linear velocity and angular velocity. So our linear velocity, remember, is still v. Angular velocity is the letter omega. Looks kind of like a rounded W. Linear velocity is equal to the radius times the angular velocity. Yep. This here, that's just a V. It's a script V is all it is. But it's linear. Technically, it's an omega, not a W. If you take a look in the packet you guys got on Monday, page 371 to 372, we're going to talk about this more next Monday, just so you guys know. We're going to clarify the angular velocity stuff. But take a peek at the stuff. We're going to go over it more on Monday and have definite homework on it on Monday. We're looking at talking about more angular velocity Monday, some more graphing and stuff on Tuesday. Probably review Wednesday. Next week, Thursday is going to be a unit test. Just so you guys are aware of that.